Hello, physics students. I'm going to give you notes here about pendulums. I don't know what the plural. I don't speak Latin. Come on. So I don't know. Pendula. Is that the plural? Pendulum? I don't know. You can write whatever you want there. I'm going to write pendula and see how it goes from there. Now, before we get into that, I'm just going to remind you, back to our simple harmonic motion notes, that the signature of simple harmonic motion is this, where the second derivative of position is equal to negative constant times position, right? So basically, acceleration is the same as position, but for the sign switch and the constant here, right? So if your position is over here, then your acceleration is going to be the other way, and it's directly proportional. The more you get away from equilibrium or the zero position, the more acceleration you're going to have. So it's a restoring, there's a restoring force. With the mass on the spring always wants to get back to equilibrium. Whether if you've stretched the spring, then it wants to go back this way, and then if you've compressed it here, it wants to push back to that equilibrium position. Okay, so now we're going to start with what is called a physical pendulum. Probably when you hear the word pendulum, not when you heard the word pendula, because nobody actually says that, but when you hear the word pendulum, you probably think of like a mass on a string, right? And a physical pendulum is like for pendulum. Oh my goodness, can't talk and write at the same time. I was going for that, I guess. The physical pendulum is something that instead of being like a string with all the mass at the very, very end, it's some kind of physical object that can swing back and forth. So for example, if you put this like on a nail or something like that and you gave it a little displacement off to the side, it would rock back and forth like this. This is a physical pendulum. A simple pendulum is the string with all the mass at the very end. But we're going to start with this more complicated example. And I'm going to just make one that's, it doesn't have to be any kind of nice shape. Make one that looks like this lump here. Where do you want the axis to be? It could be anywhere. It can't really be down here. It's got to be above here so that, we're imagining that you could give it a little bit of a tilt and it's going to rock back and forth. So let's say the axis is here. Does not have to be, in fact, well, it can't be at the center of mass, because the center of mass of the object is the thing that needs to get like displaced off to the side. If the axis was in the center of mass and you rotated it a little bit and then let go, it would just stay there, right? Because there wouldn't be any, the gravitational force would not want to restore it back because it would already be axis at center of mass. So let's say that's the axis there, and this is the center of mass here. And let's say that right now we'll call this thing can wobble back and forth, and we'll measure this, that'll be like the angular displacement, right? And let's call this distance from axis to center of mass. Let's call that distance D. You can call it R, whatever. But I usually use a D for that. Okay, so if we were going to make a force diagram for this thing, then we would pin all the forces on the center of mass, right? And there would be a force from the axis, like kind of holding it up, sort of like a normal force. The important thing for us is that this is the center of mass, that the gravitational force here in the direction that this thing can rotate, oh, that's like there, going back to the center, or the axis there. The only part of the gravitational force that can make it rotate is the part that wants to make it go this way. Or in other words, if you're thinking of for torque, torque is equal to R times force, which here, the torque from the force of gravity is equal to times the sine of the angle between them. So here that's going to be mg, that's my force here, times d, that's my r, times the sine of theta, right? That's like my force times radius times the sine of the angle between them. And I want to convince you that, there should be a negative sign here, just like there's a negative sign in force equals negative kx. There should be a negative sign here because if you make this go off this way, right, if your angular displacement is this way, like counterclockwise, then the torque will be clockwise. And likewise, if your angular displacement is this way, clockwise, then your torque is going to be counterclockwise. So it's always going to restore. It's going to want to go the other way than whatever your angular displacement was. So we should have a negative sign there. Right? Now, what did we do here? If we think about the analogy to a mass on a spring, then at this point, right now I just have like force equals this, right? That's kind of like having this equal to that. I'm kind of at that stage of the development of things. So torque, if this is the only torque acting on this, well, torque by Newton's second law in rotational form is equal to I alpha, right? Torque equals I alpha. Right. And I'm going to make a couple substitutions here because alpha is angular acceleration. That is the second derivative of angular position, right? Just like regular acceleration is the second derivative of regular position. So that right here, I'm going to turn that into second derivative of angular position. And I'm going to divide this I over to the other side. And I'll have that like so for now. And maybe at this point, if we're paying attention to things, see that here the signature of simple harmonic motion is second derivative of position negative constant times position. Second derivative of angular position equals negative a constant times, oh, so close. If this was just angular position, if that was just theta, then we would have it. Then we would have, oh, that's simple harmonic motion. And that is why the small angle approximation is important. Because as long as we stick with small angles, I can make this substitution that instead of sine x, I can just write x. So instead of sine theta, I can just write theta. So by the small angle approximation, now of course this only works if you're going to displace this like a ton, like way more than 15 degrees, then you really shouldn't be going anywhere near the small angle approximation. So by the small angle approximation, sine theta is approximately equal to theta. So that gives me that. And that second derivative of position equals negative constant times position. That is that signature. It's like the thumbprint of simple harmonic motion. That's what we look for when we suspect that something might be a case of simple harmonic motion. And we suspected this. I mean, a pendulum, certainly there was a chance, right? Because it definitely like has an oscillatory kind of motion. Back and forth, do, 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 do. So, where does that leave us? Well, this is true, and then when you have to go through, and I'm sorry to tell you this bad news here, that you do need to be able to do this. This is a thing kind of like deriving the acceleration of a rolling object down a ramp. This is a thing that you need to be able to do. But once you get to this point right here, where you get the differential equation, then this is what you get to do. You get to say, by analogy to a mass on a spring, now for the mass on the spring, the omega was equal to the square root of this, right? And then, of course, the period of a trig function is equal to 2 pi divided by omega, which is 2 pi times the reciprocal of that. So you can jump straight from, like once you get this, this is the thing that's going to be underneath the square root sign upside down, just like this k over m ends up here in the period equation, right? Period equals 2 pi times the square root of m over k. There's the k over m. So you can say here, by analogy to mass on a spring, the period of a physical pendulum is equal to 2 pi times the square root of I, its rotational inertia, over mg d. And what does that d stand for? That is the distance from the axis to the center of mass. How about that? Pretty cool, huh? If that is a physical pendulum, what about the so-called simple pendulum? Well, now that we have our fancy equation for a physical pendulum, this is just a very simple case, pun intended, I guess. So this is not to be confused with angular momentum, L. But a simple pendulum, we just have mass, all the masses here, and this is like a massless or a string that's of negligible mass compared to that. So we know that for a physical pendulum, 2 pi times the square root of I over mgd, that's the period there. So can we apply that to this? Let's see. So period of a simple pendulum is 2 pi times the square root of, what would the rotational inertia of this be with respect to this axis here? Well, it's a point mass, right? All of the mass is there, so it'd just be like ml squared, right? It's all of it is at that full distance, ml squared. And then on the bottom I've got mg, and then what's the distance from the axis to the center of mass? Well, that's just the length of the pendulum. And that simplifies to the masses cancel out and one of the L's cancels out, so it's 2 pi times the square root of L over G. Cool. That's the period of a simple pendulum. And that's really all you need to know. Those notes are pretty quick. Just so you know about what is and what is not on the equation sheet. This is like a general true statement. This is just telling you something you've known from pre-calculus or maybe earlier, that the period of a trig function is 2 pi divided by omega, like the thing that shows up in here. You knew that already. And then period of a mass on a spring, that's on there. And this period of a simple pendulum, that is on there. This is not on there. So when this comes up in free response, you do have to go through the process of deriving that. All right, that's all I got for you right now.